Okay, so last week we stopped with precipitation reactions, and this week we're going to talk a little bit about today we're going to talk a little bit about complex ions. And we're going to find that we're going to find that many metal ions, especially the transition metal ions, form what we call complex ions. And they do that by forming coordinate covalent bonds with either molecules or anions, which have lone pairs, okay? And cations. It should be molecules, cations, or anions, but it's usually anions. There's very few cations that'll do it. Now, this type of bond, we've already talked about. It's a Lewis acid-base reaction. We talked about that in chapter 16. So the coordinate covalent bond, a lone pair on one atom from a molecule or ion, is going to form a coordinate covalent bond with an empty orbital on the metal. And so that's why we call these coordinate covalent bonds, and these things are going to form our complex ions. So for example, the nickel 2 ion, okay, it can react with ammonia, neutral ammonia, to form a complex ion. And we're going to write the complex ion in one of two ways. Now, the proper way really is to write it like this, where we have the nickel, we have the 6 ammonia, and then there's square brackets which indicate that it's a complex ion, and then the charge. Now, I will tell you that most chemists are just going to write it like this because they're going to understand that this is a complex ion, okay? But usually, if you're unsure, you would put square brackets around them. We're just going to write it then as the nickel and then the 6 ammonia and the +2 charge. So basically what happens is that we have the nickel ion, and each of the ammonia has a lone pair of electrons. Well, those lone pair of electrons are going to overlap with an empty orbital within the nickel and form a coordinate covalent bond. In fact, it's going to do it 6 times. So you can see that there's 1, 2, 3, 4, 5, and 6. Now, in the last chapter that we cover, we're going to come back to complex ions, and we're going to say that this thing has a coordination number of 6. It has a coordination number of 6 because it formed 6 coordinate covalent bonds. It's going to have an octahedral molecular geometry, right? It has 1, 2, 3, 4, 5, 6 regions of electron density around the central atom. So it's going to form an octahedral molecular geometry. Here's just an example. So if I have nickel 2+, just an aqueous solution of nickel 2+, it has this teal color, I guess you would call that. But if I add just some, let's say, Windex, which is just an ammonia solution, once I add enough, it goes purple. And then no matter how much more I add, it'll just remain purple. As I start to add it, it's going to start switching color. It's going to start going from this green, and it's going to slowly switch to different colors until finally it reaches this purple. Okay, so we can see that they have very distinct. This is why solutions that contain metals are generally colored, because they're forming these coordinate covalent bonds. They're forming these complex ions. Again, you can see here water is acting as one of these things, which we're going to call ligands here in a second. Okay, so then we basically replace the water with the ammonia. And that's because the ammonia has much stronger coordinate covalent bonds than that of the water. So the ones that form the strongest coordinate covalent bonds, they're going to be the ligands that are attached to the metal. Now, a complex ion is simply an ion formed with a metal ion with a Lewis base attached to it by the coordinate covalent bonds, as I've already explained. The ligand is the Lewis base, the electron pair donor. So in the last case, water was a ligand, and then it was replaced by the ligand ammonia. A complex is simply defined as a neutral compound containing complex ions. We'll come back to that. So in other words, there's going to be 2 complex ions, one positive, one negative, one anion, one cation, and they're going to form a neutral salt. So we call that a complex. Okay, so here was the nickel, this time with cyanide. So if you put in a nickel into a solution that has a 1-to-1 molar ratio with cyanide, we're going to form this complex ion. But if we put nickel into a solution that contains twice the molar ratio, right? Excuse me. It's going to form this complex ion. And if we put in 3 times the molar ratio than that of the nickel, it'll form this complex ion. So you can see they're adding one at a time. And if we increase it by 4 times, so in other words, 4 times the amount of cyanide compared to the nickel, it's going to form this. So it is a step-by-step process until we get up to this, the final complex ion. Now, no matter how much more cyanide I add at this point, it's never going to add another cyanide. It's always going to stop at 4 cyanides per nickel. Now, are you supposed to memorize that? Absolutely not. These things are going to have formation constants associated with them. And when you look at by looking at the table of the formation constants, you'll be able to tell exactly how many ligands of a given type will associate with that particular metal ion. Okay, so you don't have to memorize them. You always have the tables of chemical data, even on an exam. So you'll be able to just look it up and figure out how many ligands there should be for that particular metal ion. Now, we're always going to work with an excess of the ligand. So we're not going to have to worry about all of these intermediate steps along the way. We're just going to have to worry about the final complex ion that's formed, and that would be given by this equation here. So again, we're always going to make sure that this is an excess. So this will always be the limiting reagent. So we'll always deal with the full complex ion in the problems that we do. So like I've been alluding to, it has an equilibrium constant, and we're going to give it another fancy name. This time we're going to call it KF. So KF is just the formation constant, equilibrium constant for the formation of these complex ions in aqueous solutions. So this here again was the nickel and the cyanide. Note that this is an ion. All ions are soluble in water. Let me repeat that. All ions are soluble in water. No matter how big this thing gets, if it's an ion, it's going to be soluble in water. So the formation constant expression then, the KF, is going to be equal to the products raised to the coefficient in the balanced chemical equation, right, divided by the reactants, each raised to the coefficient in the balanced chemical equation, so nickel to the first and cyanide to the fourth, just like we've seen in chapter 15. Okay, and the KF for the nitrogen cyanide complex ion is 2.0 times 10 to the 31. So do you think the formation of the complex ion is favored, or is there going to be more product or reactant? Is the formation of the complex ion going to be favored? Keenan, what do you think? Is the formation of the complex ion going to be favored?
Can you hear me?
I can hear you now.
Okay. Sorry, I thought I clicked unmute. I think it should be favored because it's quite a large number.
Oh, it's huge. So
Yeah.
in other words, there's almost none of this left. Well, if this is in excess, let me rephrase that. If this is in excess, because this is so huge, there's basically no nickel left.
Yeah.
Okay, now that's going to become important. So yeah, these complex ions are very much favored. In fact, here's a table of just some of the different complex ions. The smallest one is 10 to the 7, which means, again, basically everything went to product. We're going to use that to our advantage. Otherwise, we would have some horrific math to do, okay? So again, it means basically these large KF means everything's going to the complex ion, and very little of the free metal then is going to be left in solution. And as I was saying before, you don't have to memorize what each metal ion forms a complex. Just look at a table. So if silver reacts with cyanide, it's going to add 2 cyanide. Okay, we'll deal with the charge again in the last chapter that we cover, you'll actually be able to tell me what the charge on each one of these are, but we'll get to that then. So again, usually most metals will always have the same number of ligands, but that's not always true. So here's an example with the nickel. It will only take up 4 cyanides, but it'll take up 6 ammonia molecules. So again, you don't need to memorize any of them. Just look it up in the table, okay? Okay, so when CN then is added to the solution, the nickel, you would expect most of the nickel ion to react to form the complex ion. Again, just saying that, hey, look, there's almost no nickel left. Now, if we wanted to solve this then, okay, so this KF is large, it's huge, okay? So that means that when we actually set up the equilibrium constant expression, right, when we set up the ice table, we're going to have, in this case, we're going to have a plus 4x and a plus 1x and then a minus 1x. Well, now think about it. If this goes to almost 0 and we have a minus x term, and x is basically the same size as the original concentration, there's no way we can ignore the x term. That means in this particular case, this would be raised to the first, this would be raised to the fourth. That means we would have an x to the 5th. We have a 5th order polynomial. There is no analytical expression like the quadratic formula to solve for a 5th order polynomial. The only way you could do it is to converge from both sides of the x value. And you'd have to do that 5 times. Well, it would take you a month at least to do it by hand. You could type it into a computer, but the computer is going to expect it to be as ax to the 5th plus bx to the 4th plus cx to the 3rd plus dx to the 2nd plus ex plus A, B, C, D, E, F, G equals 0. So you would still have to put it in that form before you could plug the numbers into the computer to get it out. So it would take a tremendous amount of time to do it that way. So we're going to take advantage of the fact that KF is so large. We're going to make an assumption that all of the nickel, all the metal ion, reacts to form the complex ion, so that there is none of this left, and all we have is the complex ion. So there's no metal ion left, it's all gone to the complex ion. That's going to allow us to flip the equation and look at the dissociation of it. So there's the dissociation. This is the equation for the dissociation, okay? Okay, so here we simply flip the reaction, right? So now we have the complex ion dissociating into the nickel and the cyanide. Now, why did we do that? Well, because remember what KD is going to be the inverse of KF. So that's basically, if this was what, 10 to the 31? It's going to be 1 over 10 to the 31. So it's going to go from a huge number to a really, really small number. And remember, when the equilibrium constant is really small, generally less than 10 to the minus 3, 10 to the minus 4, we're always going to end up being able to ignore the x plus and minus x terms, okay? So by doing this, we're now going to have a really small value for our equilibrium constant, which is going to allow us to ignore the plus and minus x terms, okay? So let's try an example of it. I want to know, what is the concentration of free nickel ion? So this is going to be the free nickel ion, nickel 2 plus, in a 0.025 molar nickel 2 nitrate solution that is also 1 molar sodium cyanide. And it gives us the KF value for the cyanide. And the reason we did that is we need to know what the formula is. Okay, so now, so we can see then from looking up the KF, we can see that the complex ion is going to be the nickel and then the 4 cyanides. Okay, so that means it looks like this, right? This is the formation. This is the KF expression. Remember, every K value has an associated chemical reaction with it. So if this is the KF for the nickel cyanide complex, it's going to be the nickel reacting with 4 cyanide ions. Again, you know your polyatomic ions, so you know that cyanide has a -1, okay? The name tells you, by naming this thing, it's nickel 2, so that must be nickel 2 plus. And then it goes to the complex ion. What happened to the nitrate? Why doesn't that show up here? Hannah, why isn't the nitrate shown up?
It's the conjugate of a strong acid.
Right. So this salt, nickel 2 nitrate, we throw it in water. We know it's a soluble salt because of the nitrate, right? So it's going to completely dissociate into the nickel and the nitrate. The nitrate isn't forming a complex ion with the nickel. And it's not going to change the pH or anything because, again, it's the conjugate base of a strong acid. So it's just a spectator ion in all this. It needs to be tossed out. You got to do your homework. You got to be able to recognize this. Same thing with the sodium, right? So again, sodium cyanide, according to rule number 1, sodium salts are going to be strong, soluble salts, therefore strong electrolytes. So it's going to dissociate into the sodium ion and the cyanide. The sodium isn't involved in the complex ion. The sodium is a conjugate acid of a strong base, so it's not going to affect the pH or anything like that. So all we're worried about is the cyanide. Okay, so that's why the sodium is being ignored and the nitrate is being ignored. Basically, what this is telling us is that we have 0.025 molar nickel 2 plus, and we have 1 molar cyanide. Okay. Okay, any questions so far about just understanding how to write the equation and what the initial concentrations are going to be? Okay, so if I have a 1 liter solution, we initially have 0.025 moles of the nickel 2 plus, and we're always going to assume 1 liter of solution unless they tell us differently, because that makes it easy. Then the molarities are just the moles. Okay, so we're going to assume we have 1 liter. So that means I have 0.025 moles of the nickel 2 plus, and again, that's coming from the nickel 2 nitrate. And we're going to assume that each nickel reacts with the cyanide, right, reacts with 4 of the cyanide to form the complex ion. So we need to find out, this was the initial concentration of the cyanide. So there would basically be 1 mole, if it was in a liter, it would be 1 mole of the cyanide. We're assuming that all of the metal is the limiting reagent and reacts with the cyanide, so it's completely gone. But then we need to know how much cyanide is left. Well, because that's going to be a common ion within this solution, as we're going to see in the next slide. So we started off with 1 mole of the cyanide. But we used 4 cyanides for each nickel, right? 4 cyanides for each nickel. And there was 0.25 moles of the nickel. So that means I used 4 times 0.025 moles of the cyanide to make my complex ion. Since all of this reacted to form this, again, I used 4 times the concentration of the metal, 4 coming from the number of ligands, and this being the concentration of the metal. So this was the original concentration of the cyanide, less what I used to make the complex ion from all the metal ions, which means I have 0.9 moles of cyanide left over after all of the metal reacts to form the complex ion. So what is the concentration at this point? What is the concentration of my nickel? Taylor, what do you think? What's the concentration of my nickel?
I'm not sure.
Haley, what do you think? What's the concentration of my nickel at this point?
I'm not sure.
Leah?
You would set up a molar ratio. So it says that each nickel reacts with 4 CNs. So for 1 mole, wait, am I saying this right?
Hannah, how much nickel's left?
Never mind.
I'm looking at it and I'm trying to figure that.
We just said that nickel was the limiting reagent. How much nickel's left?
All used.
Oh, none.
None, 0. It's the limiting reagent. It all reacted with the cyanide. So that's the initial concentration of the nickel now when we look at the dissociation. What's the concentration of the complex ion?
Wouldn't it be equal to the amount of cyanide?
Nope.
Okay.
Where did the complex ion come from? What was the limiting reagent?
If the limiting reagent was nickel and it all reacted with the cyanide, does that mean that there's no complex ion?
Just the opposite. You just told me all the nickel formed a complex ion.
Yeah.
So how much complex ion is there? If all nickel,
Would it be 0.025?
yes, exactly right. So if all the nickel, the 0.025 moles of the nickel went to the complex ion, meaning we now have no nickel left, so that means we have 0.025 moles of the nickel. Does that make sense? Okay, now at this point, how much cyanide do I have? What's the initial concentration of my cyanide once the dissociation starts?
Is it 1 molar?
No, that's the initial, that was the initial concentration before the complex ion. What's the concentration of the cyanide after the complex ion is formed? That's what we just figured out. So there is 0.9 molar of the cyanide. There is 0 nickel left after this reaction. We're kind of assuming a single arrow at this point, right? It's just going that way. I can even add that to that. Okay, so it is all reacting. So all 0.025 moles of the nickel reacted. So there's none left to form the complex ion. And since we are saying it's the limiting reagent, that means there must be 0.25 molar of my complex ion. We started off with 1 mole of the cyanide, but we had to use up some of it to form the complex ion. We used 4 for each complex ion, and we had that many complex ions. So it would have been the initial amount 1 minus the cyanide that we had to use up to form the complex ion. So 4 for each, and it was 0.025 moles of the nickel. So that means there's now 0 nickel left, there's 0.9 molar cyanide left, and there's 0.025 moles of the complex ion. Okay. So again, we assume that all the metal ion reacted to form the complex ion. Now we can look at the dissociation of the complex ion itself. So we just flip the reaction. Again, we now know that all the nickel, that 0.025 was all converted to the complex ion. So this is now 0.25. All the nickel reacted, so it's 0. And we just calculated that we have 0.9 molar of the cyanide left. Is everybody clear at this point? Okay, so now we're going to lose the reactant, so minus 1x, gain our product, so plus 1x, and then plus 4x. Equilibrium, we just add the initial and change, so 0.025 minus x, 0.9 plus 4x. Now we're looking at the dissociation, so we need the KD, right? Now the KD is just going to be the products, each raised to the coefficient in the balanced chemical equation, and that's what we see here, divided by the reactants, again raised to the coefficient in the balanced chemical equation. And we know that the KD value is just the inverse of the KF, right? We look up the KF, and it is 2.0 times 10 to the 31. Okay, so we looked that up. So that's simply going to be 1 over the KF. And then again, we just substituted in our equilibrium concentrations in terms of X for the products and reactants. Now we have a plus 4x term and a minus x term. Since this thing is, again, going to be really small, approximately 10 to the negative 31, right? 10 to the negative 30 something, okay? So this is going to be really, really small. That's going to allow us to ignore those plus and minus x terms. We will check it later on. So we're going to ignore them. Now all I have to do is solve for x. So I'm going to take and multiply 2.0 times 10 to the negative 31 by 0.025. And I'm going to divide it by 0.9 to the 4th. Don't forget these. Don't forget it in the original expression. And then I see a lot of students actually put it in the original expression. And then when they actually plug in the numbers, this gets lost somewhere. I don't know what happens to it. Again, this is why I want to see your work. I wanted to see that you originally understood that it should have been to the 4th, and then you just forgot to put it back, okay? So be careful. A lot of students drop these exponents for some reason when they go from the expression to filling it in the numbers. Okay, so we simply rearranged it, and now we're going to solve for x. It's 7.6 times 10 to the negative 33. Now we have to go back and we have to confirm that our assumption to ignore x was correct. And I'm just going to use the one with a smaller value. It doesn't matter that there's 4 more times here, as you could probably already obviously see from the number. But if we take 0.025 minus x, that's still 0.25 to the same number of sig figs and rounding. So these two numbers are alike. Therefore, our assumption to ignore the plus and minus x terms was valid. And there's our x term. Now remember, from the ICE table, x is the concentration of free nickel ion in solution. So that is the answer right there, is 7.6 times 10 to the negative 33 molar. So you can see that there is very, very little free nickel 2+ ion floating around in the solution. Okay. Okay. Any questions with any of that good stuff? Okay, next I want to talk about what we call amphoteric hydroxides. Now remember, amphoteric species could act as either acids or bases. So these are amphoteric hydroxides. So they can act as an acid or a base. So let's take, for example, aluminum hydroxide. If I throw aluminum hydroxide in an acid, well, the acid's going to react with the hydroxides. It's going to rip them off the aluminum, and it's going to form aluminum 3+ and then the water molecules. Now remember, there's 6 water molecules here because we're using the hydronium ion. We could write this just as H+, and then this would all of a sudden become just 3. Okay, so again, I don't care if you use H3O plus or H plus, we know that only H3O plus really does exist. Okay, now there is aluminum hydroxide acting as a acid or base. Is aluminum hydroxide acting as an acid or a base? Well, in this case, it's reacting with an acid, so it must be the base. Okay? But aluminum hydroxide will also react with a basic solution. It actually picks up another hydroxide to form this complex ion. So in this case, since the hydroxide has to be the base, this time the aluminum oxide is acting as if it was an acid. Okay? So you can see here it acted as a base because it reacted with the acid. Here it acts as an acid since it's reacting with the base. So that's what amphoteric means. Here's zinc is also forms amphoteric hydroxides. So here's an example. If I have a solution of zinc, so that's this guy right here. Here's a solution of zinc, and this is just sodium hydroxide. At first, the solution of zinc is just clear. But as I add the sodium hydroxide to it, a white precipitate forms. Well, we know that that is the zinc 2 hydroxide because most hydroxides are insoluble. And so basically, you see that white powder forming. And if you would just leave it go, it would settle to the bottom, and then the bottom would be coated with this white powder, which would be your zinc 2 hydroxide. However, if I keep adding more sodium hydroxide, all of a sudden the solution goes clear again. And that's because the zinc 2 hydroxide reacted with 2 more hydroxides to form this complex ion. Okay, we'll get to the naming part later on, but it's this complex ion. Okay, so again, we can see that the zinc will act as an amphoteric hydroxide as well. Other common metals, and you do not have to memorize these, but aluminum, the zinc 2, zinc 4, I'm sorry, just zinc 2, tin 2, tin 4, lead 2, chromium 3. There's a couple of others, but there's not many. But understand this idea of what the amphoteric hydroxides mean. Okay, so make sure you understand this. Again, do your homework. Okay, next, let's talk about combining a couple of things. Let's combine complex ions with solubility. So an insoluble salt will form specifically with certain metals. So for example, we know that well, here, we'll do this example here. We're going to find out that cadmium oxalate is actually, even though it's not in the solubility rules, I'm telling you here, right in the problem, that cadmium oxalate is an insoluble salt. And again, if you don't know, look up the KSP values, right? If it doesn't have a KSP value, it's a soluble salt. If it does have a KSP value, it's an insoluble salt, okay? So we want to know if cadmium 2 oxalate is going to precipitate out in a solution that also contains, well, let's just look at this one first. So this is just the solubility, this problem here. So we want to know, will cadmium 2 oxalate precipitate from a solution that's 0.007 molar cadmium 2 nitrate. Again, we have the nitrate. All nitrates form soluble salts, so it's not going to precipitate. Again, it's the conjugate base of a strong acid, so it's not going to change the pH. So it's a spectator ion. Same thing here. We got the sodium ion, another spectator ion, right? Our conjugate bases of our strong acids are going to be spectator ions. Our conjugate bases of our conjugate acids of strong bases are going to be spectator ions. So basically what I'm saying is I have 0.007 molar cadmium 2 plus and 0.008 molar oxalate. Does everybody understand that? Do your homework. Okay, so we have our cadmium 2 plus reacting with the oxalate to form our cadmium 2 oxalate. Okay, since this is +2 and this is -2, it's a 1-to-1 ratio. Now, how am I going to predict, without looking at your notes, how am I going to predict whether a precipitate is going to form or not? How am I going to predict? Be on today's exam. Okay, well, when we say predict, we are simply comparing Q to K. So we got to come up with Q, these being our initial concentrations. So Q again is just going to be, now keep in mind, this is not the KSP expression, right? This is the formation of the solid. This is not the KSP expression. We have to flip this reaction for the KSP expression, okay? It has to be flipped. That is the KSP expression. We got it, so QC has got to be in the same form as the KSP. So now it's just the initials, it's 1-to-1, pure solids aren't going to appear. So our cadmium was 0.007 and our oxalate was 0.008. So that means the Q value is 5.6 times 10 to the negative 5. You'll need to look up the KSP for cadmium 2 oxalate, which is 1.4 times 10 to the negative 8. So I can see that the Q value is greater than the KSP. So does that mean a precipitate will form?
Does that mean the product goes back to the reaction goes back to the reactants?
Absolutely, right? Since K is too big, too many products, it's going to go backwards. So yes, a precipitate's going to form, right? Okay, let's look at the same reaction. This time, it contains 0.2 molar. In addition to all of this, it contains 0.2 molar of the ammonia. And again, we're going to ask, will a precipitate form? Well, since this is going to form a complex with the cadmium, only the free cadmium 2 plus will actually react with the oxalate to form a precipitate. So we're first going to need to determine the concentration of cadmium 2 plus left over after the formation of the complex ion. So we got to go through this again. Notice that I'm already looking at the dissociation, right? And then we're going to have to use KD to solve it. Again, you'll have to calculate, well, this is going to be obviously in excess compared to, look at the cadmium concentration. So definitely in excess. And again, from looking up the KF value, I could see that it was going to react with 4. So again, we assumed that all of the metal, so all of the 0.07 went to form the cadmium complex ion. There's no metal left. The concentration of the remaining ammonia, well, I would assume 1 liter, okay? I would take 0.2 minus the amount that we needed for the complex ion. So that's going to be minus, well, the complex ion, there's 0.007 of them, but there's 4 ammonia. So it's going to be 4 times 0.007 minus 0.2. Okay, so that's going to give me the concentration of the ammonia. Then we're going to set up the equilibrium constant expression for KD. Again, we're going to assume that the plus and minus X terms are small, and we could ignore them. Solve for X. Go back, check that our assumption was correct, and it is in this case. And that means X then is the concentration of free cadmium in solution. So now all I have to do is plug this into the Q expression, except this time, instead of the 0.007 molar, now all I have is 8 times 10 to the negative 7 molar cadmium and the 0.08 molar sodium oxalate. So now our Q expression is going to be 6.4 times 10 to the negative 9. That is now, so again, our Q value is now less than K. So that means the reaction could actually go the other way, and I should show that on this slide too. 80, show K, P, K, reaction. So again, this is saying now it's going to go from reactants, which was the solid, to products, which were the individual ions. So no, a precipitate isn't going to form now. Okay. Any questions with any of that good stuff? Okay, that's it for this chapter. Number 65. It wants us to predict whether copper 2 hydroxide will precipitate from a solution that is 0.003 molar copper 2 nitrate, 0.1 molar sodium hydroxide, and 0.15 molar ammonia. And then it says, note that the copper 2 ion forms a complex ion with ammonia. Okay, so let's deal with just the first part of it. Let's deal with the question at hand. It says, predict whether copper 2 hydroxide will precipitate from solution. How do we go about predicting whether or not something is going to precipitate or not? What would we need to do?
You need to use a Q value.
And what are we going to do with that Q value?
Compare it to the KSP.
Yeah, right. So we're going to take Q versus KSP. KSP, not a problem, right? I'm just going to look up the KSP in the book. And so the KSP is going to be 2.2 times 10 to the negative 20. What is Q? How am I going to figure out Q?
You have the molar concentration, so just plug them into the equation.
I'm sorry?
You have the molar concentration, so just plug them into the Q equation.
Okay, now that would normally be true, except that there's going to be another issue with that. But before I get to that, I want to know, what is the Q equation? Where's the Q equation come from? Some balanced chemical reaction. So what is the balanced chemical reaction that we're going to have to get Q from?
The dissociation of copper 2 hydroxide.
Okay, now we're comparing it to KSP, and KSP is the dissociation reaction, right? So the KSP is talking about the copper 2 hydroxide, which again would be an insoluble salt, which means double arrow, dissociating into its individual ions, copper 2 plus, and then the 2 hydroxides. So, right, that's what the KSP is. The KSP would be the concentration of the copper times the concentration of the hydroxide squared. And so Q is going to now have that same look, except that instead of using the equilibrium concentrations, we're going to be using the initial. So all I need from the ICE table is I. So what is the I of the, what's the initial concentration of the copper?
No, never mind.
Why not? Why never mind?
Wait, Of the copper.
Of the copper 2 plus. What is the initial concentration of the copper 2 plus?
Is it the 0.003?
And
Or no?
and I'm going to come back. I'm going to say no.
Okay.
We'll come back to that in a second. So what about the hydroxide then?
I'm not sure. I think I confused myself. Hold on.
Okay. I'm going to tell you right now that the hydroxide is 0.01. 0.010, and don't forget to square it in this case. But I'm telling you that the copper 2 plus isn't 0.003 molar. Can anybody tell me why that's true? Why?
You have to dissociate.
Well, it will completely dissociate. Copper 2 nitrate, nitrates are strong electrolytes, soluble salts. So this will completely dissociate since it is a soluble salt. And I didn't leave myself enough room here, but copper 2 plus the 2 nitrates, okay? Single arrow, strong electrolyte, soluble salt. So, I mean, at this point, this is going to be 0.003 molar. But why isn't it 0.003 molar here? What else in this question is telling me that it is not?
Because it forms a complex ion with ammonium.
Exactly. And remember, these complex ions, those equilibrium constants, they're huge. So again, it's going to favor whatever, just like we talked about the, if we had a weak acid and a weak base mixed together, would the solution be acidic or basic? Do you remember how we answered that question? If I had a solution of a weak acid and a weak base, how could I know if the solution was going to be acidic or basic since I have both an acid and a base in there?
If it's a strong acid or strong base or weak.
There is no strong acid. I'm telling you, it's a weak acid and a weak base. We're mixing a weak acid and a weak base together. And I told you that we could determine whether or not the solution is going to be acidic or basic. How? We compared the Ka and the Kb, right? Whichever one was bigger, that's the one that wins. If the Ka was bigger than the Kb, the solution is going to be acidic. If the Kb was bigger than the Ka, the solution is going to be basic. The same principle holds true here. We have the KSP competing with the KF. But the KSP is a super small value, super small K value, right? Times 10 to the negative 20. But we know that these KFs are huge. They're big. So that means before any of this could happen, whatever complex ions are going to form first. Well, it didn't tell me what the complex ion was. So how am I going to determine what the complex ion was or is, whatever English I'm supposed to use? How do I determine that?
Well, you set up an equation or a chemical reaction between copper 2 and ammonia. And
Okay, I agree with you, right? So it is going to be, so the formation reaction, right, is going to be, and I want to separate these two things. I'm going to talk about what you're talking about down here. Okay, so you're saying that the copper ion, which is a copper 2 plus, is going to react with, in this case, we're talking about ammonia, right? So NH3. Again, aqueous, because The neutral nitrogen-containing molecules have the same intermolecular forces as water, and then it's going to form a complex ion. Oh, what's the formula of that complex ion? Didn't tell you. So what's the formula of that complex ion? How would you find it?
Well, couldn't you just relate the charges? Oh wait, never mind.
No, it doesn't work that way. This is a neutral molecule. How am I going to determine that formula? It's really, really easy.
Do you just look it up in the tables?
Yeah, right. So I have iron, I have copper 2 plus, and I have ammonia. So I look at my tables, which again, they're in alphabetical order. This time not by name, but by formula. So let's see, where's copper? So there is copper. Okay, so now we have copper. I gotta move this up. So now we have the copper, but I am looking for the ammonia. There it is. Okay, I know it's probably hard to see on here, but it is the copper and then ammonia, and then there's 4 ammonia, and it has a +2 charge. And while I'm here, I might as well take the value, right? So the KF value then is going to be the 1.7 times 10 to the 13. Okay, so this is telling me, the table's telling me the formula, so Cu, and then there's the NH4, 3, and there's 4 of them, and this whole thing has a +2 charge. What phase label is this guy getting?
Is it aqueous?
Why?
Because of the ammonia?
Nope.
No.
Real simple reason.
It's ion.
Ions are soluble. All of them. Every single one. Aqueous. Okay. Okay, and since I'm here, I'm going to get that KF value too. So that KF value, I don't know where I want to put it. Let's put it right here. So KF is equal to 1.7 times 10 to the 13. So again, to go to that point, we have 2 competing reactions. We have this one and this one. The equilibrium constant for this one is huge compared to this one. This reaction is going to win. It's going to dominate. So what that means is that it's going to use up most of the original copper that was in solution and form a complex ion, which is not part of this copper 2 hydroxide. So I can't determine the initial concentration of copper 2 until I determine how much copper 2 is actually left in solution. Now, also, as you recall from the lecture, right, we said, well, we got to actually finish this, right? There's 4 ammonia here, so this would be 4. And if we'd be setting up an ice table, we would have a plus, in this case, we'd have a -x term and a -4x term. But because this is so big, that means most of this is going to this, which means that -x term is almost as big as the initial concentration. X is not going to be negligible. We would have to solve a 5th order polynomial in this case. So how did we get around that? We're not going to be able to solve a 50th order polynomial, nor would we ever want to. So how can we easily get around that and make the math real easy?
I'm sorry, could you repeat the question? I kind of got-
Yeah, I mean, we don't want to solve a fifth order polynomial, okay? You definitely don't ever want to have to do that. So the question is what can we do so that we don't have to solve a fifth order polynomial and, in fact, make the math really easy? I'm not quite sure I understand what you mean divide by 4. Coding.
Could you use the molarity 0.15 and then times that by 4? And I don't know.
Okay. Let's look at it this way. Since this thing is huge, right? And I'm not going to be able to ignore the plus and minus x terms, what happens to this value if I flip this reaction? What's going to happen to this value if I flip the reaction?
Divided by, or 1 divided by that?
Yeah, so what's going to happen? Is it going to become big or small?
Smaller?
Really small, right? It's going to be 1 divided by 10 to the 13, or approximately 10 to the negative 13. Will I be able to ignore any plus or minus x terms if this is 10 to the negative 13? The answer is yes, right? Anything smaller than approximately 10 to the minus 3, 10 to the minus 4, obviously depends on the initial concentration, but generally anything with an equilibrium constant of 10 to the negative 3 to 10 to the negative 4, I'm probably, in anything less than that for sure, I'm able to ignore the plus and minus x terms with a very small amount of error. So we can do that here, right? Because again, this huge value is basically indicating that all of our reactants have gone to products. Well, at least for the limiting reagent, right? So here we started off with, we've established, right, that we started off with 0.0030 molar of our copper 2 plus. And the original question told us that we started off with 0.15 molar of our ammonia. Now we're making the assumption that all of this copper reacted to form our complex ion. And then what we're going to look at, by flipping the reaction, we're looking at the dissociation of our complex ion. So we're now going to start looking at the dissociation of the complex ion. And the reason we want to do that is because that then has a KD value. And right, we flip the reaction, so when we flip a reaction, all we do is take the inverse of the original equilibrium constant. So now we have 1 over 1.7 times 10 to the 13. That's going to give us 5.882 times 10 to the negative 14. So now we have a really small equilibrium constant. That's going to allow us to ignore any plus or minus x terms. So, well, we'd have to set up the ice table then. So what's my initial concentration going to be?
Is it going to be a 5.88?
Well, remember what we assumed, right? We assumed that this reaction, since this was so big, we assumed that this reaction went to completion. So this is a limiting reagent type problem. It's a single arrow. If we're assuming that it goes to completion, it's a single arrow. So this is nothing more than the limiting reagent problems that we did earlier. So which one of these are the limiting reagent? Which one's going to run out first? Do you have to do the math, or can you look at these numbers and tell me?
Copper.
Yeah, right. There's 0.003. Let's assume 1 liter, right? So there's 0.003 moles of the copper and 0.15 moles. There's literally over 100 times more of the ammonia compared to the copper. So we know then that the copper is going to be our limiting reagent. And what I'm looking for here is the final concentrations, because there's no equilibrium here. We're assuming that this all goes to products. So if all this goes to products, what's going to be the final concentration of the copper 2 plus?
0.
0. If that's my limiting reagent, there's none left. What would be the concentration of the complex ion? Now we're assuming again, I'm not leaving myself enough room here, but we're assuming that we had none in solution to begin with. When this reaction is complete, how much am I going to have?
0.003.
Yeah, this is the limiting reagent. It's a 1-to-1 ratio between the copper and the complex ion. This is all going to my complex ion, so this is going to be 0.003. Now, what about the ammonia? Is it all used up?
No.
No, so there's some left over. How am I going to figure out what's left over? So I want the NH3 left over. So it must be the initial minus final, right? So again, assuming 1 liter, we'll call this 0.015 moles. Now this is what we started with, right? So started with this. Now the question is how much did we use up, right? How many of these did I make?
4. No. Yeah.
I made 0.0030 moles of them. But how many ammonia did I use to make each one of them?
Could you use a molar ratio starting with
Well, that's not what I'm asking. I'm asking if I made this many complex ions, right? So that means I had to use that many ammonia molecules at least. But how many ammonia molecules did it take to make each one of these?
did it take 4 molecules? Like 4.
Took 4 each. Each one, I needed 4 ammonias. So times 4. Does everybody get that? So what's left over is what I started with, in this case, 0.15 moles. I made this many complex ions, but each complex ion required a certain number of ligands, in this case 4. So you'd plug that into your calculator, and what is left over then, what is left over is, find it, 0.138. Now this is moles, but again, we assumed 1 liter. So, right, we assumed 1 liter. Okay. So this would be our 0.138. And again, we're 2 past here. This one's going to be way past 2 past. So it'll just be 2 past. So it's going to be 0.13. So that's what's left over. Now, what we have left over then, that's what we're starting with. Because now we're going to look at the dissociation, because remember, you can't lose track. These are big problems. You got to do your homework. Okay, this is generally one of the toughest exams in the course, even more so than the final, because of these are all big complex problems. So again, you can't lose track of what we were looking for, which was the concentration of copper available to form our precipitate. So that's what's going to be left over, equilibrium, after my complex ion is formed. So now we're looking at the dissociation. And again, we did all of this so that we could ignore the plus and minus X terms. So the initial concentration then, well, we got that. That was 0.003 moles or molar. There was no copper. It all reacted to form the complex ion. And there was that much left over after we formed all of the complex ions from the amount of copper that we had. Any questions on that? Okay, so now it is just a normal ice table. We're going to lose our reactant, so minus 1x, plus 1x for the copper, plus 4x for the ammonia. Equilibrium, that's 0.0030 minus x, plus x, and 0.13 plus 4x. The equilibrium constant expression, Kd, is simply going to be equal to the concentration of our products, each raised to the coefficient in the balanced chemical equation, divided by our reactants. Again, raised to the coefficient in the balanced chemical equation, 1 in this case. Plug and chug, so this is 5.88 times 10 to the negative 14 is going to be equal to x times 0.138 plus 4x divided by our 0.0030 minus x. And this is raised to the 4th. Now again, if we had to solve it this way, this would be a 5th, right? So x to the 4th plus x, that would be a 5th order polynomial. So because the equilibrium constant is so small, we're probably going to be able to ignore the plus and the minus x terms. Again, you can't ignore all of them, you'll have nothing to solve for. You only want to ignore the plus and the minus, nothing that's times. Right? This is x times this value. These are plus and minuses. And when we do that, now all of a sudden we get x is equal to 5.882 times 10 to the negative 14. I'll multiply both sides by 0.003. And I'm going to divide both sides by the 0.138, but don't forget that's to the 4th. Plug that into your calculator. That'll give you an x value of 4.865 times 10 to the negative 13 molar copper 2 plus, since x is copper 2 plus, right? Any questions with that part of it so far? So if I just asked you this part on the exam, I could have asked you, instead of adding the solubility, I could have said, well, what's the concentration of the free copper 2 plus in a solution that contained 0.003 of the copper 2 nitrate and 0.15 mole of the ammonia? You'd be able to go through and solve it and say, hey, look, the copper 2 plus is 4.8 times 10 to the negative 13 molar. Well, this is just combining two ideas. So if that is the free copper 2 plus, and again, it's got to be the free copper 2 plus, this won't react with the hydroxide to form a precipitate. Only this will. So now that we have the free copper 2 plus, that value is going into here. So that's going to be the 4.865 times 10 to the negative 13. You would plug that into your calculator, and you're going to get a Q then of 4.8 865 times 10 to the negative 17. And so will, answering the original question, will copper 2 hydroxide precipitate in a solution that also contains the ammonia at these given concentrations? So will it form and precipitate?
Is it yes because the Q is bigger than the K?
Absolutely, right? Since Q is bigger than K, that means we have too many products. So the reaction is going to go back towards reactants, and yeah, a precipitate is going to form, right? So yes, precipitate will form. Now we could actually quantify this and would find out, well, there's a lot less precipitate formed whenever the ammonia is added to the solution, right? We could actually determine the amount of precipitate formed if we didn't add the ammonia, and then calculate it after we added the ammonia. It would just be, again, a common ion effect type problem. Okay, any questions about this? This is about as hard as they get, literally the entire course. This is probably about one of the most difficult problems, and could very easily be on an exam.
Just to sum it up, it's a
Yep.
lot of steps for side stuff. So you solve for Q, and then you plug it back in to the initial, to another ice table, solve for the molarity, and then you plug it in to find Q and then compare.
Okay, to sum it up, we were looking for the concentrations for Q, right? Now, we couldn't just use the regular copper because the copper reacted to form the complex ion. So we needed to know how much copper 2+ was actually left over after the formation of the complex ion so that we could stick it into here. But we couldn't just solve it normally because the K value is so large that wouldn't allow us to ignore the plus and minus X terms and would have forced us to solve a fifth order polynomial, which mathematically is very challenging. If you make any minor mistake, and again, it's going to be a huge equation, and the answer is going to be wrong. But we simplified it by simply assuming, since this is so big, this entire reaction went to product, and then we could calculate then simply the dissociation of our complex ion into the individual ions, giving us the equilibrium concentration of the free copper that we could then plug back in over there. So that's kind of just a big overview of what we did in this problem. Again, the only reason we flipped it is so that we then have a really small equilibrium constant, which allowed us to ignore these. Now, I didn't go back, and I missed a step, right? If I take, so I'll work with a smaller value, even though this is 4x, this is still, 100 times smaller than that value. So it's going to more influence this. So if I take 0.003 and I subtract 4.8 times 10 to the negative 13, well, to the 2 sig figs, it's still going to be 0.0030. So we checked our assumption, and it was good. Okay.
I also